sorry for the delay. We will start now our next session of talks. We will start with the Project 16 talks that were supposed to be in the morning. And the first presenter is Karla Andriani, postdoc in the group.
So thank you, Lucas, for the introduction. I'm Karla, and I'm leading the QTNano Methane team members under the supervision of Professor Juarez Silva. And today I'm going to show you some results from my postdoc for this first 2 years of postdoc, which combine DFT and Spearman rank correlation analysis to investigate methane dehydrogenation on 3D 13-atom transition metal clusters. So our team have been focused on this type of reactions in conversion of methane to methanol. However, this is a great challenge because the stability of this molecule, it has a 2D symmetry, high pKa, and so to the activation of methane towards other products depends of the abstraction of this first proton. So it's necessary a lot of energy, and this reaction occurs at high temperature. So our team here has been focused on study different type of materials as catalysts, such as transition metal clusters, oxides, and our future work we want also to investigate this type of supported catalysis, and also going to larger size of infinite systems like surface. So our goal here is to understand the whole process that starts with the desorption of this molecule towards the desorption of the products. So, however, this is another great challenge because these reactions do not occur in a single step. It involves a lot of other reactions. We can at least list down 5 types of reactions, which are CH for dehydrogenation reactions, which is the loss of one hydrogen atom in each step. The interaction, each species can interact with oxygen, for instance, to lead the product, like methanol. However, methanol can also suffer dehydrogenation, which are methanol dehydrogenation reactions. Of course, in the end, we have also the side products. This is a complex question to be solved because at least we have 21 reactions for this minimum path as well as 25 transition states. So these are going to be addressed in our work. However, today I'm only going to show you our results in the first step, which are the dehydrogenation reactions. This work has recently submitted to FUIL, and we hope to have a positive response. So we have applied PBE van der Waals corrections in FJ AIMS analysis, and beyond DFT, we also use a Spearman correlation analysis to try to address which are the descriptors that drive the desorption energy. If they are structural descriptors, magnetic, and so on. Beyond that, we also applied a method called UB-cap method, which is a unit bond index quadratic exponential potential method, which you can, with only the desorption energies and the dissociation energy in the gas phase, in the desorption phase, we can estimate the value of the activation energy barriers. So what was our strategy to deal with this problem? We proposed 3 different types of methodology. The first one is the endomical desorption of the CAGN species over the transition metal clusters. Then to address the thermodynamic effects on this type of system, we have to maintain the number of atoms. So we also investigate the effect of the hydrogen co-desorption, and to have access to kinetic properties like activation energy barriers. We use CH4 susceptible dehydrogenation, in which each step the molecule CHN was fixed in the first position. So now I will show you some of our results by applying the example of iron clusters. When it show here the adsorption site in regardless adsorption site preference, we can see here that the hydrogenation process that decreases the number of hydrogen atoms from CH4 to C. This species tend to occupy larger CH sites, which follows also the decrease of the distance between this molecule of CH4 toward C. Also, this is followed the tendency, the increase of the coordination number between the carbon and the transition metal. Thus, along with this preference, we found that the hydrogen bond distance and the formation of CH4, the bonds that are direct interact, CH bonds that direct interact transition metal suffers for elongates, while the other bonds that do not interact with transition metal are shortened. And we have also a different bond angle in comparison with the gas phase molecules. So as to try to dissect another property drive, these standards, we also calculate the charge transfer by electrodensity difference and also the Ricci charge. And showing here we have the long hydrogenation, the charge transfer increase from the transition metal to the CH species, which shows that this is a localized process and is maximized or favored when we enhance the interaction of the D metal to the P states of CH species. So to try to understand better, we also calculate the project density of states. And here I'm showing only the case for the two extremes, nickel, but iron and cobalt have the same comportment, and copper. So here I have shown you this is stage 4 to C. Here the D states for nickel and the D states for copper, and the P states are represented in purple. So you can see here we have increase of the coupling between the P states and the D states of the metal. And this is increased along hydrogenation and has is showed for and all that's present the same behavior. However, when you're looking here for copper, this is not well observed. Due to the complete occupation of the states of copper, this energy, the energy of the states, the energy window is shortened. So the enhancement of SPD is not so effective. So in conjunction, these properties explain the adsorption energy trends for the systems, which increase in magnitude along the hydrogenation process. So we can now propose an interaction mechanism of these molecules in this type of catalysis of clusters, which is the charge transfer from transition metal to the CH species, the enhancement of SPD hybridization, and also the number of unpaired electrons, which increasing with the decreasing of N. So how about the effect of hydrogen co-adsorption? As I show here this, in these panels, the effect of hydrogen co-adsorption induce add new S states from the hydrogen, for the additional hydrogen, and then when these S states hybridize from the P states from the carbon, for instance, there is a split of these states, and then the hybridization occurs is enhanced with the G states of the metal. This is only a local effect and a small effect. So as shown here, that the interaction energy only increase by a small value in comparison without the hydrogen co-adsorption. So how about the other properties? The other properties are not affected at all, which confirms that this process is local. So this was our result for the prototype global configuration of the lowest energy configuration for the dissolved species. Now you want to understand if these results are applied for also the other high energy configuration. For that, Jonathan, which is my collaborator in his machine learning team, he did a Spearman correlation analysis to try to address which are the main features capable to modulate the adsorption energy. And we have, in agreement with our previous result, we also found that decrease of the distance between the carbon and the transition metal, the increase of the charge transfer, as well the increasing of the SN, which corroborate with our results. So again, to try to understand the energetics of the Siga-4 hydrogenation, we plotted this type of graph, which is the relative energy for the reaction. So you can see here that we have some similar behaviors for iron, copper, and nickel. So for copper, iron, cobalt, and nickel. For copper, this behavior is different. However, if we compare here the distortion of the binding of CH4 is stabilized thermodynamically stable for all classes. However, it has a slight preference for nickel in comparison with the other ones. However, to try to understand now the snaps of this mechanism, we investigate now the elementary reactions between each CH hydrogenation step, which are shown here. However, if this state is the reactant and the product, if this line is above the 0, we have isothermic reaction. If below is the other, we have here the endothermic reactions. This is a little bit different from the previous results because these are the elementary steps, and we now can calculate the activation energy versus the energy between the reactant to the transition states. Now, to try to have an overview of our results, these are plotted together, our both results from Siga-4 hydrogenation and as well the activation energy barrier. This is what chemists really like. So these are the relative reaction energy in regard to the reaction progress, which is from the adsorption process to the dehydrogenation reactions. As shown here, we have a slight preference. This process is slightly preferred on nickel systems with a large activation energy barrier for the last step. And in comparison with copper, for instance, this is not so thermodynamically favorable. However, we can see here for the formation of CH3, we have some isothermic reactions here occurring for like nickel and cobalt, but this is not observed for copper. Or I can show here that we have two types of graphics here. In the dashed line, we have now the effect of hydrogen co-dissociation on the activation energy barriers. It's only a small effect, so only the dissociation energy decreases with the co-dissociation. So our conclusions here about the dissociation properties, we propose a mechanism that drive the trends, which depends of charge transfer, the gradual arrangement of speed coupling, and the number of the pairing electrons. The hydrogen co-dissociation has only a local effect. However, it's sufficient enough to increase a little the dissociation energy. To enhance more speed coupled, the new states which are split towards less negative energies. So all steps stage for the hydrogenation are thermodynamic, slightly preferable on nickel cluster than on iron or cobalt. However, they present a similar activation energy barriers, which slightly decrease with hydrogen co-dissociation. So, how can we can connect these results with our experimental results available? So, for copper cluster, we have found that the largest value for activation energy from the step formation CH to C, which is in line with the experimental finds the carbon copper-based bacteria are difficult to form carbon depositions. So this is what I can show you. To have some questions about the method that we use to calculate the activation energy barriers, you can ask me or can ask me in the poster section. Thank you so much.
Okay, so we're now open for questions. Anyone?
Thank you for the presentation, Karla. This last conclusion you have, that's the copper-based materials have as main feature resistance against carbon deposition. Is this an explanation why copper materials are harder to poison with?
Yes, yes, this
So
this is in line with the experiment. I forgot to say, but when I was writing the article, System Literature Information, we have it has a group in United States, Professor Mentroth. And he synthesizes all this type of material. So we have a direct comparison from our results, from the experimental results, from this type of cluster from N to 2 to 16. So we can do this type of connection.
So that's why everybody's looking for copper, because
Yes.
Okay.
So if you have asked me, which are if you're going to use directly in catalysis, I will say nickel, with an alloy of nickel or cobalt or nickel or copper. This is another project that we are going on here.
Thanks.
Thanks, Karla. My question is about the methodology to include the coabsorption, hydrogen coabsorption in your systems.
Okay.
In that case, you start with the absorption site for methane, and then you start to...
I'm sure it does better, right?
yes, explain better.
Yeah.
And then you start to, I don't know, remove a hydrogen, but put that hydrogen where? Close to the
okay.
absorption site? Or?
Okay, here, this the first step is, I think it's more easily. From the lowest energy configuration of the first step, we now we add the hydrogens, but randomic. We range all the possible configurations, and we have found that from that we observe that some configuration that release hydrogen, molecular hydrogen, or maybe one atomic hydrogen. So we choose, it's not the scope of its work. We exclude these configurations. You only treat the configuration that all hydrogen were absorbed. So if CD3, we absorb 1 hydrogen. CD2, 2 hydrogen, CH, 3 hydrogen, and C, 4 hydrogens. So here we consider all the clusters, but the lowest energy configurations are also when these hydrogens are closer to the molecule. In the next step, we fixed the molecule, and then we absorb just 1 hydrogen to investigate these reactivation energy barriers and exclude the diffusion process. So this was the... No, to exclude, we fix that. No, we just observed that the lowest energy configurations, the hydrogen was really close to, so we don't go further to the diffusion process hydrogen in the clusters.
Okay, so do we have any more questions?
Karla, what were the possibilities of using cluster in combination with other materials, zeolites, for example, that increase the affinity and selectivity of the clusters?
This is actually this is our our future goal, to combine this result to other supporting oxides or mimic or other type of materials. For instance, copper is not good as nanocluster, but we have known that copper at MMOs can activate methane. So non-oxygen and other aluminum can change this type of materials.
Okay, so let's thank Karla again.
Thank you.